Good morning. Take two. I think I was just 10 minutes into something and then it was disappeared, so I'm going to start over. Love when that happens. Hi. So, we're going to talk about Newton's second law, in particular, applying Newton's second law. Newton's first law says that when the net force acting on something, on an object, is zero, the object won't accelerate. You've heard that in more colloquial terms. It says objects at rest tend to stay at rest, and objects in motion tend to stay in motion until acted on by a net external force. I say, that when objects are in equilibrium, they don't accelerate. Equilibrium means net force applied equals zero. So what will this object do? This object has a net force acting on it. So what will this object do? Well, conceptually, the answer is accelerate in the direction of net F. Notice I'm using this word accelerate. That's the only word we can really accurately use here. This object, this 2 kilogram mass, will not, by definition, move this way. We have no idea what direction this object is moving right now. It might be moving in the opposite direction of that and slowing down. It might be moving in this direction and speeding up. It might be moving in some totally different direction and both speeding up and changing direction, or slowing down and changing direction. But all we know for sure is that this object will accelerate in this direction, in the direction of this 10 Newton force. Well, Newton's second law allows us to say not only that, but it allows us to quantify the rate at which this object will accelerate, and we do so via that expression. Right? Newton's second law says that an object's acceleration is proportional to and in the same direction as the net force applied to it, and is inversely related to the object's mass. So the more net force, the more acceleration. And those two things increase or decrease at the same exact rate, I guess you could say. But the more massive an object is, the less it will accelerate. All right? And this idea we should really talk about. All right? M equals mass, what we'll call inertial mass. This idea of inertia, oh boy, sidebar. This idea of inertia, okay? Objects, every single object resists acceleration, right? Objects tend to keep, you've heard this before, right? Newton's first law. Objects tend to keep doing what they were doing before, all right? And the more massive an object is, the less it tends to accelerate. Let's say we're keeping the net force, let's say we apply a constant net force to lots of different objects. Well, the more massive objects are, the less they will accelerate as a result of that force. More massive objects are more difficult to accelerate. More massive objects have more inertia. So inertia is, quote, resistance to acceleration. Every single object in the universe has some resistance to acceleration, has some inertia. And, well, while inertia is not a quantity, it's not measurable, it's an idea, mass is measurable. And mass, some say, is a measure of inertia. So the more mass objects have, the more inertia they have. So those two words can almost be synonymous, except for the fact that mass is a quantity that's measured in kilograms or grams or whatever you want to call it. And inertia is an idea. But there are these dastardly questions that say, hey, which one of these things has the most inertia? And they'll give you lots of different objects with lots of different masses, and maybe like lots of different speeds and lots of different, I don't know, colors or temperatures, or they won't do that. But inertia only is dependent on mass. All right? The more mass things have, the more inertia they have. Okay? Okay. So I'll show you in a minute that we can think of mass in two different fundamental ways. One of them is this idea of inertial mass, which is to say that by the nature of objects, the nature of objects is to resist acceleration. Okay, so that's one nature of mass, the fact that mass resists acceleration, mass has inertia. Okay, sidebar over. Let's get back to it. Now, what will this object do? Well, Newton's second law says we can state slash quantify the acceleration of this object. This object will accelerate A equals net F 10 newtons divided by 2 kilograms. You see? This object will accelerate at a rate of 5 newtons per kilogram. Okay. Well, what's a newton? Well, some of you will know that a newton is a kilogram meter per second squared. So that means, well, a newton per kilogram is, oh, good, a meter per second squared. A meter per second per second. This object will change velocity at a rate of 5 meters per second each second. That's what acceleration of 5, this is a 5. The other ones are S's. That's what 5 meters per second squared means. It means that velocity will change at a rate of 5 meters per second per second. Okay, and furthermore, we can say in this direction, right? In the direction 37 degrees below the horizontal, because that's the direction of the net force. And Newton's second law is a vector equation. So net force and acceleration must point in the same direction. Okay, that's one approach. Pretty straightforward. The other approach is to look at this maybe in, quote, more convenient, in a more convenient set of directions. And more convenient means this. Well, guess what? Lots of surfaces are, quote, horizontal, right? And as a matter of course, we do a lot of, say, lifting objects up and lowering objects. So using directional coordinates that are horizontal and vertical is pretty convenient for us in lots of cases. And so when forces don't point in those directions, what it can be very convenient to do is to say, well, there's a component of this force that points in one of my convenient directions, and here's a component of force that points in another convenient direction, and it almost by rule, yeah, by rule, we should really talk about components of forces in perpendicular directions, because then whatever the x component of this force does has nothing to do with the y component, and vice versa. And particularly, any x component of force has nothing to do with acceleration in a y direction, and vice versa. So we can actually calculate, right? We can say that, well, there's an acceleration of this object in the x direction that depends on the force in the x direction and the object's mass. There's no such thing as mass in the x direction. All right, and so how do we calculate the component of this force? Well, I want you to note that we can make a right triangle. Oh gosh, that didn't happen. So we can take this, just ungroup it, would you? There, look, we can take this and make a right triangle out of these two vector components, these two x and y components, and their resultant is the whole force. And so we can apply trigonometry and say, well, the x component of this force is the whole force, right? This is force F. The whole force times, in this case, the cosine of the angle between the force and the x component. And if you don't believe me that fx equals f cos theta, then write an expression for, with this triangle, cosine theta, or cosine 37. Well, in this case, that happens to be 10 newtons. What I haven't said is divided by m. That's 10 newtons cosine 37 degrees over 2 kilograms. Well, I happen to choose a nice friendly angle for you. And a lot of test writers will do the same thing. And I bet on any reasonable reference table, the sine and cosine of 37 and or 53, the component, or the complement of that angle, those sines and cosines are provided for you because they're easy. 37 and 53 degree angles are part of a 3, 4, 5 triangle. We've got a hypotenuse of 10, so this is going to be a 6, 8, 10 triangle. So this A in the x direction, if you don't believe me, type it into your calculator. This is 8 newtons over 2 kilograms. That's going to give me 4 meters per second squared that away. Okay. We might also, if we're talking about acceleration in the horizontal direction, we might as well talk about acceleration in the vertical direction, because there is a component of this force in the vertical direction. And so AY is Fy over m, and Fy is going to be F sine theta. There's over m. This is 10 newtons times the sine of 37 degrees over 2 kilograms. And like we said, that happens to be, in this case, a 6 Newton force vertically divided by my 2 kilograms. That gives me 3 meters per second that away. Okay, so that's what this object will do. Well, it will do each of these things, which is doing this, right? Because, look, 4 meters per second and 4 meters per second and 3 meters per second are 5 meters per second at 37 degrees below that horizontal. So we've answered the question in 2 ways, which you wouldn't have to do, but I'm showing you there are 2 approaches that yield the same result. Okay? All right. Now, that's as basic, sort of as basic as you could get, but typical scenarios maybe look something more like this. They say, look, here's a thing. It's a box. It's a crate. It's sliding across a rough floor. There's pushing and pulling and people and heavy, and so we want to analyze. I mean, the question, well, a standard question will say something I'm not going to put up there yet, but in a basic sense, the question is, so what does this object do? All right. Well, the answer is we can do some analysis to find that answer. So what we will do is we will draw what's called a free body diagram. And a free body diagram is a representation of the forces acting on an object. All right. And from that, what we can do is write net force statements. And from those, we can relate the acceleration of the object to things like the net force pointing on it or applied to it in different directions, and the object's mass. And so let's draw ourselves a free body diagram. Here's the object. But wait, the object is a crate. It's not a dot. Yeah, okay, but for most of this, or for this unit, what we will consider is not the fact that objects have shape and that pushing on them in different locations can actually make different things happen. Like, you know, maybe this pushing up here starts to make this thing tip over. Well, we don't want to talk about tip over yet. All we want to talk about is linear accelerations. And so we simplify objects as considering them as point masses, and forces all act on the object's center of mass, treating it like a single point. Okay? And so what forces act on this object? Well, let's see. It's heavy. What's that mean? Well, heavy probably means that heavy probably means, that's better. That's a vector. That this thing weighs a lot. All right. And so, well, I'm going to write that like this. FG, F subscript G. And so that gravitational force, FG, gravitational force, weight. And this is exerted on the object by Earth's gravitational field. Gravitational field. Yes, fine. Let me, if I may be so bold, subscript this. Okay, good. Okay, so that takes care of the heavy part. Rough, a rough floor. Rough. That means that, well, that there's going to be a, if this thing is sliding along that way, that means there's going to be a friction force that points that way, that opposes that motion. So FF, friction force. Yes. And exerted on object by surface over which object moves. Yes, fine. Okay. Yeah. All right, come on. You got to subscript that. I mean, now we're just being picky. Boink, boink, boink. Okay, great. So we got two. Let's see. Oh, one pulls. Here's the pulling person on the right. I'm going to call that T. Why not P? Well, T, we're going to call tension. Tension force. Do I have to keep saying force? And this will say exerted on object via a rope, cable, wire, string. Now, not necessarily, it's not the rope that exerts the force. It's this person that exerts the force, but the rope is the means by which the force is conveyed. Okay? So notice I'm saying exerted on object by a surface, on object by the earth, on object by really this person here, but via that rope, so we call it a tension force. Okay? Okay, there's the pushing person over here on the left, and I'm going to take a little liberty here and say, doesn't it look like he's sort of pushing downward? Yeah, I'm going to say the push looks like this. You can't make an arrow point at the dot. Oh, I can, and I did. I'm going to call that an A. A? Shouldn't that be a P also for push? No. A means applied force. A. Applied force exerted on object by something that pushes. Yeah. All right. So the big deal here is a push. When you the idea of applied, we call that push. All right. Push. This is usually like a pulling. Tensions usually look what we call pushes. I mean pulls, and applieds are pushes. Okay. All right. Okay. Well, let's see. Oh yeah. Here's the other thing. Guess what? Look at this. We got a downward gravitational force. We've got a component of this applied force that points downward. That says this thing would accelerate downward, but it doesn't. It's on the floor. It doesn't accelerate downward because the floor pushes it upward. All right, so there is a force. Oh no, capital N sounds like newtons, but it's not. This capital N is called a normal force exerted on object by the surface with which the object is in contact. Don't worry, don't worry. Oh no, that was the worst thing that's happened today. Okay there? Pause. So look, we get a normal force, which is about surface contact. We also get a friction force, which is about surface contact. But, well, normals are always there when surface contact happens. Friction might be there. For most objects that are simply sitting there on horizontal surfaces, there is no friction acting on the object because there's no potential motion, all right? But if an object is in contact with the surface, then there must be what we call a normal force. All right, basically, gravity pulls this object down onto the ground, so the ground pushes up on the object. That's a Newton's third law application. Okay, so you need to get familiar with these forces. These are the forces that basically everyone talks about. All right, and I like to use a horrible acronym that says when you're trying to figure out which forces act on an object, you can run through a checklist. W, A, N, T, F. You want near forces or something. I don't know, right? Those are the 5 forces that perhaps are acting on an object at any time. Are there other ones? Sure. These are ones that are, what we haven't talked about is, well, what if there's a magnet involved? Okay, that's maybe not the most standard thing. What if there, yeah, sure. Are there others? There are others. These are for tons and tons and tons of situations, perfectly wonderful examples of 5 different forces that might act on an object. Okay? Okay. Now, there are some rules for different forces. All right? That's here. Rules for different forces. 1, F, G. Always points straight straight down. And by straight down, you know what we mean? We mean toward Earth's center. Okay? Okay. That's one. That's one. 2, W-A-N. Okay. Normal forces always point perpendicular to the surface with which an object is in contact. I'm not a great typer. Perpendicular. Oh gosh. There. 3, friction, or FF. Well, friction, fine. No, FF. Always, watch this. Haha. Pew, pew. Parallel. Like along the surface. Yeah. So the big application there is, or a nice application there is, let's imagine an object that's on an incline. Okay. Well, gravitational force is going to point straight down. Friction is, if this thing, let's say this thing is just sitting there. Objects can do that, right? Just sit there on hills. That would have to happen because there's a friction force that points up the slope along the incline. And the normal force doesn't point up, it points perpendicular to that surface. Okay? And then the pushes and pulls, the tensions and the applieds, those can happen in whatever direction you want. You can push an object in whatever direction you want. You go ahead. All right? There's no rules about that, but these are hard and fast rules about directions that 3 of our specific forces always point. Okay? One more thing we ought to do is say, okay, this free body diagram is all well and good, but then what do we do with it? Well, what we do with it, I'm going to take this, no, not that part, but fine. Copy, copy. This won't work, watch. Yeah. Oh, fine. Lovely. Get, stop it. Give me. So what we will do with this free body diagram is we will use it to write a net force statement, or actually to probably write two net force statements, because we can now see the forces that act on this object in sort of lots of directions, but just primarily what we're focused on are the forces that act in two perpendicular dimensions, the ones that are, well, remember, this object was something sliding across a horizontal floor, so that's a direction that we're interested in. And the one perpendicular to that is by definition the other direction. I've chosen sign conventions that are common. Right is positive, up is positive. All right, and now what we're going to do is say, well, here's what I would say. We're going to write a net F in the X direction statement. Okay, and here's how we do that. Well, there's a tension force that points in the positive F direction. Do you want to explicitly say there's a positive there? Sure. There's a friction force that acts in the negative direction. This has no x component. This has no x component. Now, A happens to have a component like this, AX. And it happens to have a component like that, AY. I'll identify this angle as an angle theta. All right, what we're doing is saying there's A. You can draw it like this if you want. There's AX and AY. You can draw it like this if you want, and here's AX and here's AY. I like to do it like this lots of times. In this case, I've done it like this, but notice I'm drawing the same size components in the same direction every time, okay? So that AX component points in the positive direction to the right. And those are all of the forces acting on this object in the X direction. Well, Newton's second law says that A is net F over M. The functional way to use this in many times is to, or in many cases analytically, is to say, just algebraically, let's write this a different way, net F equals MA. So here is the sum of the forces, T minus FF plus AX, that equals MA in the X direction. The one step further I would go is probably to say, how do we do AX? Well, that's going to be A cosine theta. And then the question is probably, it's either what's this object's acceleration, and they'd have to tell you this and this and this and this and this, or what's the object's mass, and they'd have to tell you the other stuff, or what's t, they'd have to tell you everything else. So one of these things will be an unknown, all right, but we now have a statement that can be used to find our unknown. Okay, similarly, we could write a net Fy statement. And that would look like this. Well, there's a normal force pointing in the positive y direction. There is a Fg pointing down. There is an Ay pointing down. Those are all of the forces in the vertical direction, and those must correspond or play into or be, create the whatever vertical acceleration this object has. I'll give you a hint. Guess what the vertical acceleration of this block on a horizontal surface is? It's probably zero. It's definitely zero. This object is not going to accelerate upward or downward. It's just not going to happen. So AY in this case would probably be zero. I'd go one more step. Maybe I go a couple more steps. This AY is going to be A sine theta. And here's another rule. Let's go back to our rules. Gravitational forces, as you probably know, depend on two things. They depend on objects' masses and the strength of the gravitational field that objects are in. Okay, so we probably go ahead and say that this is n minus mg equals, minus m a sine theta equals may, where again ay is probably 0, but we don't need to pump that in right now. So now we are writing net force statements. All right, the things we're trying to get done now, or the steps we're trying to, the processes we're trying to get comfortable with are the idea of drawing free body diagrams, being able to read a scenario, or be told something about a scenario, and then therefore identify possibly what forces act on an object. And guess what? It's not always all 5. I was pretty slick, and I picked one where it was all 5, though. So, and after that, I mean, the reason we draw a free body diagram is so we can write net force statements. Okay? And the reason we write net force statements is, in many cases, to figure out either what acceleration an object has or how much, one of the forces is in order to create this or that condition. Okay? Okay. We'll get lots of practice as we move forward. Fairly well.